Good afternoon. So we will continue our discussion on volumes of evolution with another method, the so-called shell method. And at the end of this lesson, or as part of this lesson, we're going to put these things together and compare the two methods and emphasize why we actually need both methods. I kind of alluded to the reason why in the previous lesson, but we'll take our time to discuss more the reason why we have the two methods, because what I like you guys to accomplish is when the time comes to solve a problem like this, when you have a function and you have to compute, let's say, the volume of revolution given a a region given by a function of 2 and then an axis of rotation, the idea is to actually know how to decide which method to use. In some cases you can use either of the two methods, but the more interesting problems are those in which clearly one method is suitable because clearly one integration variable is suitable, and the variable of integration that you want to use actually dictates the method, not the other way around. This is one of those things that again tend to be confusing in calculus too. So I'm going to repeat this a couple of times as we move along with examples toward the end of the section, namely that the starting point of a problem like this is which variable of integration do I like to use? Do I care about it? Do I have a preference one way or another? And if I do have a preference, that variable of integration that you choose dictates the method. So in fact, let's write it down as a remark in anticipation to this important aspect. The variable of integration that you choose decides which method, washer or shell method, or slice, right? So slicing or shell method. So which method you will use. The variable of integration, not the other way around. People tend to kind of jump ahead and, say, well, if I want to use X, then I'm going to use the washer method. If I want to use Y, then I'm going to use the shell method. But, both methods can be used in terms of X or Y, depending on the axis of rotation. So, and then what I wanted to say also is that this lesson obviously will take more than one lecture. So, allocate more than, allocate at least 2 lecture times for this section. So let's move on with the topic at hand, right? So the shell method. So the main idea is, let's look at this example here. So take a moment to write down this generic function, the graph that I wrote here already. And imagine that this time around, the axis of rotation is the y-axis. And we're going to use a different method of approximating the volume. Normally, if I were to use the slicing method, you will basically cut this region across the, perpendicular to the y-axis. But this time, let's imagine we scoop outer shells. So basically, we approximate, in the shell method, we approximate the volume by adding thin pieces in the shape of hollow shells. So basically, you can make an analogy with peeling an onion or a telescope, for example. So imagine, this is kind of like an exaggeration because the telescope doesn't, you don't have that many outer shells. But if you imagine, for example, that you have a cylindrical object like a telescope, and you basically expand it. So let's say this is a telescope that is actually folded in, and then you expand it. So now you have what you have here on the left is basically an outer shell in the form of a hollow cylinder this time around. And then you expand it further, and you expand it further, and so on and so forth. So basically, instead of adding slices to come up with the whole volume, you basically peel outer shells until you exhaust the volume. And then the question, and you integrate over this sum of the volumes of each outer shell. So in this case, if the rotation is about the y-axis, a typical edge of the shell at coordinate x. So basically the split will be about the, over the x-axis this time around, right? So a typical shell, margin of the shell at position x will look like this. So let's say this is the x coordinate, and because we're going to have a Riemann sum, which is the limit, which is, Riemann sum, that we take a limit as the number of points in the partition increases, the thickness of this shell will be dx. So that means the nearby point here will have coordinates x plus dx. Or the thickness, like I said here, will be dx. Just like in the slicing method, except now, again, you don't cut the slice like a loaf of bread over the axis of rotation, but you scoop outer shells. And this is the margin of the outer shell, if you want, because this is the rotation about the y-axis. So let's do it like that. On the left, basically let's see if I do this. So basically the shape, if I were to draw this outer shell, it will look like this. Let's see if I manage. I'm gonna write it separately. But this is the idea. This is where it comes from. This is a typical shell. And I'll show you all of these things with Maple as well in a different video. So once again, a typical shell, if I were to take it away outside from the main graph, looks like a very, very thin cylinder with thickness dx, as I said before. And if you view it from above, it will look like a very thin annulus, right? Like two circles, concentric circles, again with thickness dx. So what's important in terms of how we actually approximate the volume of this outer shell is the radius, right? The outer radius and the inner radius. So because the thickness is dx, the outer radius of each shell is going to be x plus dx. Because the rotation is going to be in terms of, because it's gonna, in this case, the rotation is about the y-axis. Again, this will change if we switch the rotation with a different axis. But again, if you look back to the picture here, the outer radius is x plus dx, the distance from the origin, because the axis of rotation is the y-axis here. So over here on the picture, so that's x plus dx. And the inner radius is the x coordinate. So the inner radius of each shell is x. A typical shell, right? There's many of them until you exhaust the full volume, right? Starting from A to B. So how do we actually write down the volume of each shell? Well, we also need the height, right? Because we need to use the formula for the volume of a cylinder. So let's call h the height. And by the way, in this case of mine, the height will be f of x, right? I mean, because the rotation is going to be about the y-axis. So in this case, the height will be f of x. But I'll keep it unspecified for now because, again, it doesn't have to be in terms of x, as you will see later. So then the volume of the shell is basically the difference between the volumes of two cylinders. So we're going to have basically the volume of the outer cylinder, so the volume of each shell is going to be the volume of the big cylinder, which is the area of the base, pi radius of the base x plus dx squared times the height, minus the hollow part, which is again in the shape of a cylinder, of radius x, so pi x squared times dx times h, the height. Now we can pull out pi h, and expand this. So this is going to be x squared plus 2x times dx plus dx squared, and then minus x squared if we pull pi h out. Now x squared cancels, and keep in mind what you see here, the volume of this shell, is basically what comes in each term of the Riemann sum. And remember, as we take the limit of the number of points on the partition of these Riemann sums, dx goes to 0, and higher order terms that depend on dx can be neglected. So this quantity basically can be discarded because it's even smaller. Basically, if dx goes to 0, dx squared goes even faster to 0. So that doesn't contribute anything to the limit when we take the Riemann sum. So with that being said, then this is the stuff we integrate when we compute the volume here. Now, as I said before, in this particular case, h is f of x. So basically, when I find the volume of the object by rotation here about the y-axis with the shell method, is going to be 2 pi. We can put that outside. The integral from a to b. The height, which is f of x, or let's start with x, right? So it's going to be x here, and then times the height, which is f of x. This is because the rotation is about the y-axis, and the function is given as a function of x. But generally speaking, the formula for the shell method is that the volume is 2 pi, the integral with the appropriate bounds, of the height of the shell times the radius. Again, I really emphasize these generic formulas because depending on the case, it will be an integral in terms of x, like in this case, or y, depending on your axis of rotation. And then the bounds of integration, of course, depend on the context, right? So this is the generic formula that kind of covers all these possibilities. So with that in mind, let's move on with examples on the second page. Oh, one more thing before I move on, just to compare. Remember the washer method. The generic formula for the washer method on the previous section was pi integral with appropriate bounds, outer radius minus inner radius. Okay, each of these two formulas can be integrals in x or y depending on the axis of rotation. And I don't want to say which one is which because you need to know right when you look at the figure. I mean, like once you look at the figure and how you rotate the graph, then it should be pretty clear whether it is above with respect to x or y. So let's stay tuned for the second page. Okay, so let's look at an example which I think we did before. I mean, in terms of the shape of the region. I'm not sure if I did it, but anyways, we did something similar before. So the region determined by y equals x third and y equals x about the x-axis. So the axis of rotation is horizontal now, unlike my generic example in the previous page. So let's use both washer and shell method and see that the volume, I mean, just to see that the volume is the same depending on, but regardless of the method you use. So we're going to do two pictures here. So one for the washer method. Well, let's start with the shell method actually, and then we'll get back to the washer method. So the graph of y equals x looks like this, and y equals x third, like that. And again, let's say we're looking for x positive, right? So that we're looking just at the positive region. The intersection is between 0 and 1. It's at 0, 0 and 1, 1. And the region in question is the one enclosed by these two curves. Like that. Okay, now if I want to use the slicing method, the shell method, the interval of integration is going to be perpendicular to the axis of rotation. Because when you do these scoops in the form of a shell, when you scoop out these shells, each shell is parallel to the axis of rotation. So each shell is parallel to the axis of rotation. So therefore, as you scoop out these shells to exhaust the volume, then you basically integrate over the y-axis. So a typical shell is going to be horizontal in this case. The edge of the shell is like this. Like that. Right, if you imagine the rotation here. And as you move on with all other shells to compute the volume, obviously you're going to move along the y-axis. So that's the main idea. Once again, the interval of integration is dictated on how you actually approximate this volume. So try to visualize this object as this is rotated about the x-axis. You scoop out outer shells, and as these shells come up and form the volume, you move along the y-axis. I mean, each margin of the shell sits over the y-axis. So in fact, we can write it as a remark in the shell method. So for the shell method, the interval of integration, the axis where that integration takes place, is perpendicular to the axis of rotation. So basically, if you want to compute this volume using integrating with respect to y, then you have to use the shell method, because the slicing method will force you in this case to integrate with respect to x-axis, as you will see later. Okay, now once you decide that your variable of integration is y, then we need all functions in terms of y. So all the curves should be functions with respect to y. So I view y equals x as a function of y, so this is my function. And then for the other one, I got to solve for x, cube root of y, that's going to be the other function. All right, so now how do we express in terms of y the radius and the height? Well, pay attention here that the radius of the shell is going to be y, because it's in terms of y, it's basically the y coordinate, the distance from the point to the y-axis, to the x-axis. So the radius of the shell is going to be y. The height of the shell, which is horizontal in this case, well, the height of the shell comes from the difference of two x coordinates in terms of y. So the distance from that edge to the y-axis sits on the graph x equals y cubed. So the x coordinate is cube root of y. And the distance from the other point on the line y equals x is x equals y. So the height will be the difference between the two. The bigger quantity is cube root of y, and the lower quantity is y. It's very important to understand the coordinates of each point on the graph, how you refer to them, right? So this height again is horizontal. It comes from the difference of two x coordinates, but these x coordinates are in terms of y because our integration is with respect to y. And now we come with the formula for the volume, 2 pi the integral from 0 to 1, that's the interval for over the y-axis, radius, which is y, quantity height, which is cube root of y minus y. Always allocate enough time in the beginning to set up the integral correctly, because that's more than half the battle. Then it's just computation. So in this case, it's just the power rule after we simplify a couple of things. So cube root of y is y to the 1/3. Distribute 1 plus 1/3 is 4 over 3. And then minus y squared. I've got the y. So, and then we're going to do the power rule. 4 over 3 plus 1 and then 1 over the same thing, minus 1/3 y to the 3 between 0 and 1. Let's see, y to the 4/3 over plus 1, that's 7 over 3, and then 3 over 7 is in front of it. Plug in 1, and then if we plug in 0, we get this 0. So 3 over 7 minus 1 over 3, multiply by 3, that's 9, minus 7 over 21. Makes it 4 pi over 21. All right, so pause if you need to redo these steps, or do the picture with your own hand and then analyze again to see if you understand clearly what goes on in terms of how this looks like, how you set it up basically. All right, so let's say that you want to integrate with respect to x. So let's say we want integration with respect to x. Then I must use the slice method. So this is basically the main idea of why we use two methods, to give us the freedom to use the variable of integration we want. In this case, we might not have much of a preference, but you will see in the next examples that you may have a preference. But that's the idea. If you want to integrate with respect to x, then you use the slicing method, because in this particular case, because the axis of rotation is horizontal, then each slice, when you compute the volume by adding the slices, you move over the x-axis. So let's do the picture again. Let's see. Yeah, let's do the picture again. I was worried a little bit if I have enough room, but I don't need the room on the left, so. Same axis of rotation. Kind of like that, I guess. And now you do slices. So that means each slice, each margin of the slice looks like that. Now, again, if you rotate it, by the way, that's why it's called a washer, right? Because it's, if you view it from above, so, or from the right, it looks like that. Right, we have an outer radius and an inner radius. Okay, but now the integration, like I said, is with respect to the x-axis. So each washer is identified by a typical coordinate x, and we have, like I said before, we have the out, and by the way, now we use functions with respect to x, because the variable of integration is x, so the top function is y equals x, the bottom function is y equals x3rd. The outer radius is the y coordinate in terms of x, coming from the line y equals x. So that's going to be just x. The inner radius corresponding to the hollow part, let me see if I can, I made a kind of a mess here, but the inner radius is over here. And that's going to be the y coordinate on the function, which is x3rd. All right, so on the formula for the washer method, the volume will be pi, the integral from 0 to 1. Here it happens to be 0, 1 because it's the same, but it's whatever the domain is over the x-axis. Outer radius squared minus inner radius squared. So in my particular case, that's going to be x squared minus the inner radius, which is x3 to the power 2. So actually this tends to be maybe a little bit faster, right? It's a little easier integration. I mean, it's a, yeah, just a much more basic power rule here. So power rule 1/3 x third minus 1 over 7x to the 7 between 0 and 1. Plug in 1 and 0, and that's pi times 7 over minus 3 over 21. Shouldn't be a surprise, 4 pi over 7 over 21. So again, the variable of integration is dictated in the end by the method you use and the axis of rotation. If the axis of rotation was vertical, then the variable of integration is the opposite. It would have been y for the shell method. Excuse me, it would have been x for the shell method and y for the washer method. That's why, in order to not to get confused, essentially remember how you make these slices and how you compute the volume by adding each slice, or shell in the case of a shell method. With the slice method, you move along the x-axis simply because the x-axis is the axis of rotation. So just for clarity, we're gonna write down these 4 cases just to be clear, with a generic example at the end. But before we do that, I want to go over one or two more examples in which the choice of which variable of integration we want is much more strict, because it's impossible to integrate with respect to the other variable. So stay tuned for the next page. Oh, by the way, at this point, if you don't have time to follow this in a single sitting, you can stop here, do some examples from the homework, and continue on another sitting for the rest of the video, because again, this is intended to come, be covered in a typical 2-lecture meeting rather than just one. So before I actually show you a more complicated example, like I said before, in which I'll have a problem for which the variable of integration is not much of a choice, I want to do actually one example similar to the previous one, in which the axis of rotation is actually vertical. So previously, remember, we had an example with the axis of rotation being horizontal, the x-axis. So remember, in that case, the shell method meant integration with respect to x or to y, and the washer method meant integration with respect to x. And I want to show you that if we change the other axis of rotation, if we change to a vertical axis of rotation, the variable of integration switch for both methods. So we met this before, this type of region. It's a very useful, simple one to illustrate the concept. So the region between y equals x squared, x equals y squared. So a vertical and a horizontal parabola. Again, they intersect at the point 1, 1 and 0, 0. And let's see what happens if I want to use the shell method. Okay, so because the axis of rotation is vertical, each shell is going to be parallel to the y-axis. So the margin of each shell is going to be like this, right? So that's going to be the shell. I'm not going to sketch it to not make a mess here as you rotate it around the y-axis. But as you exhaust the volume, you realize that these shells basically move over the x-axis. So these margins of the shell, if you want, move over the x-axis as you scoop up these shells to compute the volume. So that means the integration is going to be with respect to x. It's very important to decide first, before you do any integral, before you set up any function, it's important to figure out the variable of integration right after you decide the method. And if you're happy with that variable of integration, which is x in this case, then you proceed with the method. If not, you switch the method from shell to washer or vice versa. Okay, so because we decided over the x-axis, then both functions should be in terms of x. One of them is already in terms of x, the other one needs to be brought in terms of x, so that means you solve for y, and then square root of x is the other function. Now, the formula for the volume is going to be 2 pi the radius of the shell times the height, and we just have to put this in terms of x now. The integral is from 0 to 1. The radius is going to be x. It's not always x, by the way. It's different if you have a different axis of rotation. But if the axis of rotation is y-axis or x-axis, the radius is always either y or x, depending on the case. But you'll see other examples later. So the radius is x, and the height comes from a difference of two y coordinates. It's whatever the y value is on the top function. The top function is x equals y squared, but the y value is root x. So that's going to be root x minus the hollow part, right? So the, minus the, not the hollow part, minus the part below the other graph, which is x squared. So that is the height of the shell. And we do this with the power rule. Again, we have to write this as powers. That's going to be x times x to the 1/2 minus x times x squared if we distribute the x. Combine and then integrate. Let's see, 3 over 2 plus 1 is going to be 5 over 2. 2 over 5 in front of it, minus 1 over 4 x to the 4 between 0 and 1. And that's going to be 8 minus 5 over 20. Simplify by 2, and that gives me 3 pi over 10. So let's do the same with the washer method. Again, I'm doing both methods just to see how the variable of integration changes from one method to another. Okay, so let's copy the graph again. Axis of rotation again is y. I mean, that doesn't change. And if I want to use the slicing method or the washer method, each slice will be horizontal now. Imagine you rotate this and then you basically have your loaf of bread, which is in the form of a donut if you want, right? Like that. I don't want to make too much of a mess, but that's the idea. Again, if you view this from above, you should visualize it like this. And because slices basically are cut over the y-axis, this means the integration is with respect to y. And now we have to write both functions in terms of y. So that means the function y equals x squared should be viewed as a function x equals square root of y. And then the other one is already in terms of y, x equals y squared. Again, be careful to measure the outer radius and the inner radius carefully, right? So the outer radius is here, comes from the vertical parabola, which is here. But of course, in terms of y, that x coordinate is square root of y. So outer radius is square root of y. And the inner radius is over here. And that's going to be from the other function, which in terms of y, that's y squared. So that's x equals y squared. So the inner radius corresponding to the hollow part is going to be y squared. And now we set up the formula, pi, the integral from 0 to 1, outer radius to the power 2 minus inner radius to the power 2. And if everything is correct, we should obtain obviously the same answer. One half y squared minus 1/5 y fifth between 0 and 1. Plug in 1 and 0. 0 and 1 are the best bounds when we teach, because it's faster to compute the integral at the end. So obviously 3 pi over 10. So we're going to finish with 2 more examples. One is kind of trickier, but just to see basically how how this formula can be adapted to more complicated examples. But so two more examples. The first one is one in which clearly the choice for the variable of integration is going to be obvious. So you won't have the choice of two methods. So stay tuned for the next page. I'm not sure it's going to be the last one, but one more for sure. All right, so suppose, and I want to mention before I go over this example, this isn't a typical problem that I will actually give in exams or quizzes or maybe homework, but not in tests. Because I'm not going to it could be trickier to graph, maybe not this one, but in general. And I just want to make the point though why we have two methods, because in many cases you do have a strong preference of whether you integrate with respect to one variable or another. You could still, in this particular case, I could make it to be impossible to do it by one method, but in this case you could do it with both methods, but it's clearly more tedious if you use one method versus the other. So this is basically, again, a horizontal parabola. If you flip the role of y of x, it's like a parabola open to the left, because you have a negative coefficient of y squared. And we can compute actually the intercepts with the y-axis by factoring this out, just to make it easy to graph it. So if we pull out -3, I made it to factor nicely so I can have a nice domain of integration. So this factors into y minus 1, y minus 3. So basically, if you sketch this, these are the y-intercepts. So this is 1, let's say 2 in the middle here, and then 3. So that's 1 and 3. The vertex of the parabola is also 3. You can compute it by differentiating here. So that's -6y plus 12. That gives you 2 for y. But if you plug it in, then the x coordinate is gonna be 3. So 3 here. So this is how it looks like. So we're looking at the region basically enclosed by this parabola, the y-axis, which is the x equals 0 here, mentioned here in the problem. And I want this to be rotated about the about the x-axis. Okay, so do I use the shell or the washer method? And so that's the key thing in this class that I want you guys to get. You don't flip a coin and say, I'm going to use this or other. Before you decide a method, ask first. The first question is, do I want integration with respect to x or y? Do you even care? Well, this is given as a function of y. And if you decide to integrate with respect to x, so if you decide with respect to x, you will have to get y by itself. And that kind of looks ugly already, right? I mean, it's not impossible to get y by itself, but it comes from a quadratic. You're going to have a square root that depends on x. It's going to be basically clearly more tedious in that particular case if you want to integrate with respect to x. A more complicated matter is, you will see actually in another example at the end, is you will have two branches with plus or minus. When you solve for y, you got to make sure which branch you're using when you set up the formula for the integral, and so on and so forth. So there are plenty of reasons that you may prefer to integrate with respect to y. But then what does that mean for the method? Well, because the rotation is about the y-axis, if I use the slicing method, so because each slice is going to be perpendicular to the axis of rotation, then integration is going to be with respect to x. And you don't want that. That means you must use shell method. Again, if you want indeed integration with respect to the y-axis, because then each outer shell, let's draw a typical outer shell, the edge of the outer shell here, again, which is going to be rotated like that about the x-axis. That's move over the y-axis when you exhaust the volume. So a typical outer shell is identified by a y-coordinate between 1 and 3. And then you can proceed with the formula, right? So let's see, the radius of the shell is going to be y, and then the height of the shell, well, the height of the shell is going to be the x-coordinate in terms of y, x as a function of y, right? So in this case, the height is going to be just the function itself, minus 3y squared plus 12y minus 9. And that's it. You can proceed with the volume now using the shell method. So 2 pi, the integral from 1 to 3, y quantity, so that's the radius times the height, which is minus 3y squared plus 12y minus 9 dy. We're going to do a power rule here. Minus 9y. Minus 3 over 4, y to the 4, 12 over 3, y third, 9 over 2, y squared. This is going to be a little bit messier, so let's set up the two parentheses, and you can compute yourself to check it up. So if I plug in 3, that's going to be minus 3 times 81 over 4. I don't think I have enough room here, so plus 4 times 27. And then minus in this parenthesis minus 9 over 2 times 9. So that's inside the big parenthesis. Sorry for the mess. Minus 3 over 4 plus 12 over 3 minus 9 over 2. How about you compute it as an exercise to finish it up? You should obtain everything. I mean, you should simplify in the end to 16 pi. You can use the calculator if you want. Okay, so I think I'm going to finish with one example, and in that example, I'm going to move on to the next page just to see a trickier example that can still be done in both ways, but I'm going to focus on how you set it up just to make sure people understand how they actually set up this inner outer radius, the height, and so on and so forth. So in this case, I want to do the integrals. I'll leave it as an exercise. I'll give you the answer. It's still the power rule, it's just a little bit messier than this one. But before I move on to the last page, let's emphasize the main idea with which variable of integration you use at any given moment of time. So if the axis of rotation is horizontal, then washer method means integration with respect to x. Shell method means integration with respect to y. If axis of rotation is yeah, so this one was just the previous case. If axis of rotation is vertical, then it's the other way around. So washer method, integration with respect to y. Shell method is integration with respect to x. All right, so stay tuned for the last example and the last page. Okay, so this is my last example. In this case, if you notice already, the axis of rotation is not going to be the x or the y axis. I'm not going to insist too much on these problems, but I want to point out that the method we learned doesn't apply just for x and y axis, for axis of rotation. It applies for any horizontal axis or any vertical axis. So it can be any line as long as it's horizontal or vertical. So in this case, the axis of rotation is horizontal, y equals 1. There it is here. And the function to integrate, to rotate, or to, one of the functions to determine the region that is rotated is again a horizontal parabola, x equals y minus 3 squared. The vertex is over here when y is 3 and x is 0. And if you cut the parabola with x equals 4, if you replace x with 4, you get two values for y, right? Because when you take the square root, y minus 3 is plus minus 4. So y could be minus 4 plus 3, plus minus 2, I'm sorry. So is minus 2 plus 3, which is 1. And the other version is 2 plus 3, which is 5. So that's the reason for these bounds 1 and 5 over the y-axis. So this is the region, let's emphasize it here, that is rotated about the y-axis, about the y equals 1. Okay, so in this case, I would still prefer integration with respect to y. I'm going to do it with respect to x just to see that you can still do it, although it will be a little bit more tedious. And I won't compute the integrals, but I just want you guys to focus on how you set them up. All right, so remember, don't refrain from guessing whether it's going to be the shell or washer method. So forget about that for a moment. Let's start with integration. Let's start with a variable, right? So we want integration with respect to y. Then you decide the method. The variable of integration decides the method. So if I want integration with respect to y, it cannot be the slicing method because the axis of rotation is horizontal. Slicing method means cuts vertical perpendicular to the axis of rotation. So that's going to be the slicing method. So that means if I move on with the slices, that will basically be integration with respect to x. So if I want integration with respect to y, then I have to think in terms of the shell method. The rotation is still with respect to y, so I have to scoop out shells, and then each shell in this case is going to be horizontal. So a typical shell is identified by a typical y coordinate, which varies between 1 and 5. All right, so if I want integration with respect to y, that means shell method. And then I have to think in terms of what is the height, what is the radius of the shell for the formula. Well, the radius is going to be, now here, this is the problem. I mean, this is where you have to be careful. The radius is not going to be just y. So look carefully, the radius is not up to the x-axis. The radius is only up to the line y equals 1. And the distance from the margin of the shell to the x-axis is actually y. But that's not the radius. I gotta subtract 1 from that distance to obtain the radius. Always, of course, measure the radius from the edge of the shell to the axis of rotation. And in this case, the axis of rotation is not the x-axis. So it's not going to be y. So then the radius in this case is going to be y minus 1. What about the height? Well, the height, not much to say. Well, I mean, there is something to say with the height as well, because the height now is gonna be the distance from the y to the vertical axis. So let's look at it like that. This is the height. It's a horizontal shell, so that's the height. And the distance from the y-axis to the point on the graph is going to be the value of the function, the x-coordinate, which in terms of y is y minus 3 squared. But the height is the difference from 4, right? So, and y minus 3 squared. So from x equals 4 and the y-axis, that distance is 4, obviously. if we subtract y minus 3 squared, which is the x coordinate here on the graph, that's going to be the height. So 4 minus y minus 3 squared. All right, so then the integral to solve is going to be 2 pi integral from 1 to 5. Okay, the radius, which is y minus 1, times the height, which is quantity 4 minus y minus 3 squared dy. You can use Maple or Wolfram Alpha if you want, or if you have patience, you could do it by yourself. The answer should be 128 pi over 3. But focus on how you set it up, because that's the important part. All right. How would you set up the other method? Let's say you want to integrate with respect to x. I'm going to sketch again the picture because it's kind of a mess here. So this is the axis of rotation. This is x equals 4, 1, 3, and 5 over here. Okay, with the slicing method, so if you want to integrate with respect to x, well, things are a little bit trickier. Now, notice if you slice it, if you use the slicing method, that's basically the typical slice, which corresponds to an x coordinate, which is now between 0 and 4. And I'll have to think about outer radius, inner radius, but those are given by these two branches of the parabola. So I have to get the parabola in terms of x. So I solve for y minus 3, and it's plus minus root x. There are two branches, one with plus, one with minus. So there's an upper branch, 3 plus root x, and the lower branch, 3 minus root x. So obviously the one on the top, this is y equals 3 plus root x, and this one is 3 minus square root of x. And how do we compute the outer radius and the inner radius? Once again, make sure you keep in mind that your axis of rotation is not the x-axis, but it's y equals 1. So you need to subtract that 1. So this will be the outer radius. Excuse me. This is the outer radius up to the axis of rotation. But the outer radius, if you look carefully, is the difference between the y coordinate on the upper branch, which is again 3 plus square root of x, and the distance from the axis of rotation and the x-axis, which is 1. So therefore, the outer radius is 3 plus root x minus 1, which of course is going to be 2 plus root x. Inner radius again is a difference in the same manner, right? So let's see how I show you here so that I don't again have a mess. This little segment here, over here, is the inner radius. That's R in, right? So that's the hollow part when you make this rotation. And again, that's going to be the difference between the y coordinate from the point on the graph, which is 3 minus root x, and the distance from the axis of rotation and x-axis, which is 1. So R in is 3 minus root x minus 1, which is of course 2 minus root x. And after that, you're done, I mean almost done in terms of setting up the integral, right? So pi, the integral now over the x-axis, which is 0, 4, the outer radius squared minus inner radius squared. So here it'll be 2 plus root x squared minus 2 minus root x squared. Take it as an exercise or use some computer algebra system, and if you've done everything correctly, it should be the same answer like before. Now, for example, in this case, Would you prefer with respect to x or y? It's a tough sell. I'm not sure. I mean, in both cases, you have to do some algebra. I would say that still the y variable is easier because I don't have to deal with these two branches. I mean, might be a little bit more trickier on the second version, so maybe it's still the y variable. So that's it for these two methods, and we'll discuss more details in the office hours. And that's it for today.